Good afternoon, class. Today we're going to look at piecewise and quadratic functions. Normally I start this lecture by discussing piecewise functions, but I think I'll do something different today. I feel like my life is in a rut, so I'm going to change things up today, and we'll discuss quadratic functions. Really, the reason you're doing this is because Pearson's been having problems, and so just don't be shocked in 5 minutes if it's back down. But everything's having problems because of the Amazon Web Services outage that's affecting
the world.
Yeah, I'm not joking. It is. It's a worldwide outage.
I'm not joking.
You sound like you're being sarcastic.
Okay, so the last time you ought to find functions.
And today we're going to look at quadratic functions. We graphed these things during the first section over graphing tools several weeks ago, but we didn't really use the word functions to describe it. But a quadratic function is any function that can be written in the form y equals or f of x equals. Remember, f of x is just a fancy way of expressing y. Ax squared plus bx plus c, where a is not equal to 0. If a were 0 times x squared, you wouldn't have that x squared term. Remember, to be quadratic, you must have an x squared term. So we're going to say that a value cannot be 0. The graph of a quadratic function is called a parabola. And a parabola is a smooth U-shaped figure. It will either open upward or it can open downward. These are referred to as vertical parabolas. We're not going to worry about drawing horizontal parabolas. A horizontal parabola would open like that. Remember, we're only interested in quadratics that are functions. If a parabola opens left-right, it fails that vertical line test. It's not a function. So we're not going to have to worry about horizontal parabolas, only vertical parabolas. Whether the parabola is opening upward or downward, there has to be a point at which the directions change. Here, this parabola is falling, it reaches a low point, and then it starts to rise again. This one is rising from left to right, and then you reach that point and it starts to fall from left to right. That point where the graph changes directions is called the vertex. And to find the vertex, we're going to have I guess I'll call it the vertex or axis formula. Vertex or axis formula. This is not a bad formula. If you remember the quadratic formula, it's the quadratic formula without the messy plus minus square root stuff. So it's x equals, and it's a fraction. How does the quadratic formula start off? Negative b plus minus all that stuff, none of that's included, over the denominator, 2a. So to determine the location of the vertex, we have this formula that will give us the x value, and then to find the y value, if you know the x value, how do you find the y value? If I said x is 3, you plug in 3 for x to find the y value. So to find the y value, just plug in that number you get using the vertex formula. I also call it the axis formula because there's an imaginary vertical line passing through the vertex of any parabola. And remember, a vertical line has formula x equals no y. So This axis, these things are symmetric about that vertical line. If I could I guess I could try to fold this paper down that vertical line, the right half would lie directly on the left half. So that's what we mean by the axis. It's technically the axis of symmetry. You fold down along that vertical line, the right half is the mirror image of the left half. When a parabola is opening upward, this is opening upward. Notice the vertex is the lowest point on the graph. When the parabola opens upward, we say that that vertex is the location of the minimum y value. It's the lowest y value. If you have a higher y value, the vertex would be higher than that. But the vertex corresponds to the minimum, minimum, y value. Using that same logic, this point here, the vertex is the highest point on the graph. It's that highest point. That means that's the maximum y value. So the vertex either corresponds to the maximum or the minimum y value, depending on whether the graph is opening upward or downward. To graph a parabola, what we're going to do is we'll use our axis formula to find the x value for the vertex. Then we'll plug that number in to get the y coordinate of the vertex. You then have to find one other point. And to do that, you can just plug in any number you want to. When you look at a quadratic function, do you see any fractions or square roots there?
See a square?
Do you see any square roots?
No.
No. Remember, what did we say? It's what Dr. Sheen told his class back in 1990 that I thought was so insightful. 2 hours later, he didn't even remember saying it, but that's beside the point. No fractions, no square roots. The domain of any quadratic function is all real numbers. So I'll say the domain. You're going to have to find the domain and range of these parabolas, so I'll go ahead and state the domain. The domain is the same regardless of which parabola you're graphing. The domain is all real numbers. Quadratic expressions don't have square roots appearing in them. They don't have variables and denominators. Now for the range, I want to look at a specific example to illustrate my logic with regards to the range. I think I'll use this one here. Okay. I'm going to talk so much that my lab's going to go back down, I bet you. But I need to talk. What I'm saying here is important. Let's say this vertex, suppose we use our little vertex formula and we get negative b over 2a. And that negative b over 2a reduces to, let's just say, 3. You plug 3 in and it gives you a y value, let's say 5. I'm just making up the numbers. To determine the range of this function, what y values are on this purple graph? The smallest y value, realize when it's opening upward, that vertex is the lowest point. That means that's the smallest y value. So the smallest y value on this graph is 5. And then the graph starts going up. The y values are getting bigger and bigger. To indicate that, we put an infinity. The smallest y value on this graph is 5. Say this y value, it's above this one, so it has to be bigger than 5. Hopefully my logic, you understand my logic why I say that's the smallest y value on the graph, so all the other y values have to be bigger. The x value, we know the x values will be all real numbers. Now wait a minute. Are you asking, do you use the x value in the range? No. You only use the y value. Now let's suppose I'm going to use the same vertex, 3, 5, but the parabola is opening downward. Okay, the parabola is opening downward. This vertex corresponds to the highest point on the graph. That means that's the maximum y value. So, remember with interval notation, you have to go small to big. The 5 is the biggest y value. You're going small to big, bottom to top. Just like this, we went bottom 5, going up was positive infinity. Here, what are we going to write first for the range? What's the small value? Negative infinity. So negative infinity up to positive 5. We can generalize what we've just seen here, and that'll help you when you have to write out the range for parabolas in the homework. Here's what we're going to say. For the range, if the parabola is opening upward, if you're looking at a parabola opening upward, you'll have a bracket, because that number we're about to write will always be included. It'll be used as a y value. That's the y coordinate of the vertex, comma, positive infinity. You're going to have to find the vertex anyway. So you'll know what that y coordinate of the vertex is. So that's the smallest y value. Everything bigger is used after that. Here, when it's opening downward, in general, the range, it'll be negative infinity up to whatever that number is there. Negative infinity, comma, y coordinate of vertex. Notice it's a bracket there after the y coordinate. That is a bracket. It's hard to tell. Negative infinity, y coordinate of vertex, bracket.
Well, that makes us a bit clear.
No one likes a smart aleck, Tony. Okay, no. I have one other thing I need to do. Here's how you're going to graph using the quadratic function tool, the vertical parabola tool. Vertical parabola tool.
Graphing tool.
Graphing tool, good. You use x equals negative b over 2a to find the vertex. Use x equals negative b over 2a.
Plug it in.
Then you have to plug that number in to find the y coordinate. To find y coordinate. I'm writing too low, aren't I? I think I can get the... And then, the second step. You'll need one other point. This graphing tool that we're using today works like the absolute value graphing tool. I'll say, choose an x value close to the vertex and plug in. I'll say, plug in a number close to vertex to find second point. You're going to need 2 points, the vertex and some other point. So we'll plug negative b over 2a in. That'll give us the x coordinate of the vertex. We plug that number in to get the y coordinate. And then we'll choose some other number that's close to negative b over 2a. So with that in mind,
see how this is like.
Here's the function. Let's write down this problem they want us to...
I just wanted to make sure.
Okay. This is number 9.
7, 8, and 9 are exactly the same. 9's the one with the messy numbers. So we want to do that if we only have time
to do one.
We can only do one if the internet holds up.
Oh, goodness. Okay, and they want us to find the vertex, axis, domain, and range. You know something? I think I'll write a little note out here for vertex, axis, domain, and range. I'm going to put a little vertex, axis, domain, and range. One of those blocks has the same answer for every possible quadratic function. I can fill in one of those blanks right there. Which one?
Flip your page.
Okay. Well, there's something here that's always the same for any quadratic function. What is it?
Put a red star out beside
Maybe I should. Right.
blue.
Oh, a red star. Oh, yeah. Look at this function. No square roots, no fractions. I remember looking at one like this the last time we were finding the domain. If your function has no square roots and no fractions, unless you're told otherwise, you always assume the domain is all real numbers. So we can fill that one in automatically. Now we're going to determine the vertex. Realize that the vertex is an ordered pair. We use the formula x equals negative b over 2a. Well, we should label A and B. We don't need C, but let's go ahead and label A and B. Remember how these things are identified. What number is A? A is the coefficient of the x squared term, so A is equal to negative 2, I agree. What about B? Well, it's a negative 12, but when we plug it in, it's going to become a positive 12. Do y'all see why that is? We have that blue negative, and then we're going to plug in negative 12, so that's going to become a positive 12. And we have a 2 times A was negative 2. Oh, goodness. So that's a positive 12 divided by negative 4. What's that giving us? Positive 12 divided by negative 4 gives us an x value of negative 3. So we know the x-coordinate of the vertex. The x-coordinate of the vertex is negative 3. If you know x, how do you find y when working with equations? You know x is negative 3. How do you find y? Okay, so we plug in the negative 3. Plugging in negative 3, we're going to get... Now, what's f of x is just a fancy way of saying what letter? Y. Now, out of laziness, I switch between f of x and y. I use them interchangeably. I'm just going to say y equals, that's a negative 2 times negative 3 squared minus 12 times negative 3 minus 10. We're plugging in negative 3 and negative 3. We know we have to perform our exponentiation first because of the order of operations. Negative 3 squared is 9 times negative 2. That gives us a negative 18. What's this negative 12 times negative 3 going to give me? What are we going to get? The negative 12 times negative 3.
We're just not talking.
Positive 36, and we have a minus 10. Negative 18 plus 36 is a positive 18. Minus 10 gives me a y value of 8. So there's my vertex. My vertex is at the ordered pair negative 3, 8.
And I stuck it into the calculator just a bit.
Oh, yes, you did. Okay, good. Now, by the way, when you use this vertex formula, you're also determining the axis equation. The axis is a vertical line. Vertical lines have equations x equals, so it's x equals -3. And you have to write that as an equation. You can't just say -3. You have to write the axis in the form x equals -3.
Let's get started with
Let's draw the. Let us draw the graph yet.
Well, wait. We got to do this. Let's type in the vertex. What was that ordered pair?
-3, 8. And since it's an ordered pair, you have to put it in parentheses. And then, here it is. They're going to have us draw the graph. So, click. And there's only one shape there that looks like a vertical parabola. Realize whether it's opening upward or downward, you choose the one that's opening upward. That's the graphing tool. And if you have a bionic eye, you can read that. It says vertical parabola tool. You click there, and they want you to label the vertex. So the first thing you have to do is plot the vertex. That vertex was at -3, 8.
Oh, shoot. -3, 7.
There it is. Do y'all see where it says it above the V? Do y'all see where in the yellow box it says -3, 8. That's where our cursor's pointed. So click that. And now move that around. Move your cursor around. Look at that, Tony. Look at that. They're drawing every possible parabola with a vertex at -3, 8. Stop that. It's getting me dizzy. So notice the instructions say plot another point. We need to choose and find another point to plot on this graph. So switch over to my paper.
I just wanted to do that before we got time.
Oh, and by the way, switch back. Let's look at the grid. Okay. It looks like it goes, 20 units in each direction? So switch back over here. You need to make sure that the number you plug in for x falls between -20 and +20. Now, some of these have something like a -30 there as the constant. If they did, and you plugged in 0, 0 is my favorite number to plug in. It's the easiest one. But if I plugged in 0 and got a -30, I wouldn't be able to plot that point. So choose an x value that's close to -3. In this case, you could use 0. I wouldn't move more than 3 units away from the vertex. Would I use something like a +10? Certainly not. That would give us a number that's way off the XY grid. But choose a number that's no more than 3 units away from the x value. You could use -2, you could use -1, 0, you could use -4, -5, or -6. Anything else would probably start getting too big or too small to fit on that XY grid they gave us. What number do y'all want me to choose? I need to choose another x value. Let's use x equals what?
0.
Okay, I'll use x equals 0, but realize when you're doing this same problem, there may be something like a -30 right here, and so you'd get something that's way off the grid, in which case you'd have to choose another number. They were just being nice to us today by giving us a 0, that -10 there. Plug in 0 for x, we're going to get y equals -2 times 0 squared minus 12 times 0 minus 10. 0 minus 0 minus 10 gives me a y value of -10. So we have the ordered pair 0, -10.
So that's the other point you were talking about.
Down here I said, use x equals -b over 2a, then plug it in to find the y coordinate. That's what we did right here. This was finding the vertex. This was finding the vertex. That's what we did right there. We found the vertex. Then we plug in another number that's close to the vertex to find the second point That's what we're doing here. We're finding a second point. Find second point. You could have used negative 1. You could have used negative 4. Choose something that's close to that x value. So now we have a secondary point, 0, negative 10.
Am I at 0, negative 10?
Is he at, what do y'all think? Is he at 0, negative 10? Yes, it's positioned at 0, negative 10. You click, then save, and check.
And that's what I wanted us to get to do one of those.
Okay, well, for the axis, we already know the axis. It's x equals the x-coordinate of the vertex. That little vertex formula we use is also the axis formula.
Here's a common mistake.
People just put in that negative 3 and...
They give you a hint that ain't that helpful. But it's an equation. You've got to write x equals. Now you have an equation. Equations must have equal signs.
The domain.
Can we type that in?
We know the domain of a quadratic function. Every quadratic function in the world has the same domain. Negative infinity to positive infinity, all real numbers.
Now, here it's going to take some
now it's going to take some thought. Let's see.
Wait
a minute. I'm drawing the little graph. Here's the graph that we just drew. I'm just drawing a little freehand sketch, and the vertex is at negative 3, 8. Is this vertex corresponding to the maximum or minimum y value? Is 8 the maximum y value or the minimum y value? When a parabola opens down, is the vertex the high point or the low point? The high point, that means that's the maximum y value. So for the range, you always, with interval notation, go small to big. Small to big. What's the small y value going to be? It's going small to big. Negative infinity. So it keeps going forever and ever down up to the biggest y value is 8. And 8 is used. I'm looking at the point that has a y value of 8. Since 8 is actually used, that's why you have to have a rectangular bracket there. Any questions on my logic? Look at my what I was trying to show here. For the range, when the parabola is opening downward, it will always be negative infinity, the y-coordinate of the vertex.
Do you use the x-coordinate?
No, you do not.
You do not.
Although the x-coordinate of the vertex, is part of the domain, negative infinity to positive infinity. Negative 3, yeah, negative 3 is between negative infinity and positive infinity. But
years ago, I remember a student saying, oh, okay, I get it. So, the axis uses the x value, and the range uses the y value. And she asked, is that always true? And
yeah,
what did I say? Always true.
I never thought of that.
Yeah.
I never thought of that. Okay.
Or
Or else you've told me that before and it just went in one ear and out the other. But that is a profound statement. A good observation. You need to finish the problem before we get timed out.
Okay.
And before we lose internet connection, type in the range, parentheses, negative infinity, 8, bracket.
Bracket, just a bracket on the keyboard. Ooh. Yeah.
Any questions there?
Now you want to go back and do another one? 8?
Let's go back to number 8. Yes. Here's an observation.
Well.
Before we go on, I want to make an observation that I didn't make earlier. It's not as relevant anymore now that we, with the graphing tool, it's not, I guess it's not so relevant, but still. When you look at your quadratic function, if your leading coefficient is positive, then you should expect the parabola to open upward. If a is greater than 0, if that leading coefficient is positive, your parabola will open upward.
Always.
Always. If the leading coefficient is negative, you should expect your parabola to always open downward. What was the leading coefficient here on number 9? -2, and sure enough, the parabola opened downward. Look at number 8. F of x equals x squared minus 14x plus 48. Oh, I like this one.
I think it's showing what you were trying.
Yeah. This illustrates that you can't always just plug in 0 as the second number. Even though 0 is always in the domain, you're going to see that we can't always just use 0. You have to be careful what number you choose as that you choose for the secondary point.
You want to write out?
Let's write out
Vertex.
Let's write out vertex. I'll put the little line. Axis. Domain. Range. And let's identify A and B. Let's identify A and B. What's A? Okay. You don't see a number there, so you assume that coefficient is a 1, and that's positive. Since that thing's positive, do we expect this graph to look like number 9?
Does it open up or down?
The A value is positive, so we expect this time for the graph to be opening upward. It's going to look like that. Oh, what's B, by the way? -14. So we're using our little vertex formula. X equals -b over 2a. We said B was -14. A was a +1. What's going to happen with those double negatives, the opposite of -14? +14 divided by, what's the denominator? 14 divided by 2, what's my x-coordinate of the vertex? 7, I agree. So over here, I can write in the x-coordinate is 7. We need to find the y-coordinate. What do we do to find the y-coordinate? Plug 7 in. So let x be 7, and then y is going to be y. We're plugging in 7. We're plugging in that 7. The exponentiation is performed first. 7 times 7 is 49. Minus 14 times 7. 14 times 7 is 98. So a minus 98. And we still have that plus 48. 49 minus 98 is a -49. -49 plus 48, that gives us a -1 for the y-coordinate of my vertex. And if you look at my brother's calculator there, sure enough, his calculator's right. It got -1 too.
Why don't you go ahead and find the second point right now?
Let's state the axis. Someone tell me the axis real fast.
Let me type this in just so it doesn't while it's working. 7, -1.
Mm-hmm.
Okay.
But now let's switch back. I want to write in the axis. We know x equals, it's that little formula, x equals minus b over 2a, and that reduced to x equals 7. So x equals 7 is the axis. What about the domain? It's always the same. Quadratic functions don't have variables under square roots and don't have variables in denominators. Therefore, the domain is all real numbers. Let's determine the, we need to determine that secondary point. All of this stuff, we found the vertex. Now we need to find the second point.
Plug in 0.
If we plug in 0 for x, what are we going to get for y? Y'all know 0 is my favorite number to plug in because it's so easy. What are we going to get for y? If we plugged in 0, we'd have 0 squared minus 14 times 0 is 0. 0 minus 0 plus 48, what is that giving me? 48. Look at that XY grid. Can you go up 48 units? Blow up the grid so they can, well, I don't know if they can see it any better than there. Do it again. Can you do it again? And y'all see, the furthest you can go up on this grid is 20. That's why I was saying you have to choose an x value that's close to the vertex. If you try to use 0, you're going to get a number that's not on the grid. Choose something that's within 3 units of 7. You could use a 6, 5, 4, or you could use an 8, 9, 10. I think I'll use a 5, unless y'all have a different opinion. I'm going to use a 5. I think 5's pretty easy to plug in. So here we are. We're going to find the second point, find another point. So I'm going to try letting x be 5, and then y is equal to we're plugging in 5. 5 squared is 25. 14 times 5, is that a 70? Minus 70. And we still have what? Plus 48. 25 minus 70, is that a negative 45? I'm getting a negative 45 plus 48, which gives me a y value of 3. So we found our other point. The other point that we're going to use, our second point, I'll say our other point is the ordered pair 5, 3.
And there's some leeway, like you could choose 6, it would work. Couldn't use 0 for the x value, but
I think 4 would still be okay. But
how
I think
do I know
3
which
might
one?
be.
Well, it's got to be between 20 and negative 20.
You got to choose an x value that'll give you a y value between whatever's used on the axis, the y-axis, and in this case it's between negative 20 and positive 20. So you choose your vertical parabola tool, and then it tells you to plot the vertex. The vertex is at 7, negative 1.
Okay.
Is that it? Yeah. And then notice, this would just be science fiction. If I could see ahead from 40
years ago.
I was going to go for it. Well, yeah, okay, 40 years ago, you're right. But it was just science fiction. Every possible parabola with a vertex at 7, negative 1. That's really shocking to me. I appreciate that. Now we're choosing this, plotting the second point. The second point was 5, 3. Is he at 5, 3? Can y'all see what point he's positioned at? Is it 5, 3? You see it in the little yellow box? Save it. Tony says that that's a yellow rectangle. not a yellow box. But
box
now that
is
I know that it
three-dimensional.
bothers him, I will certainly call it a box for as long as I
remember.
remember that it annoys you when I call it a box. I shouldn't do that. That just
Which one of
raises
these
your blood
numbers
pressure.
goes in for the
We haven't done the vertex.
the
Let's do-
axis?
Let me see. So the
No, the
parab-
axis.
the axis. We did it right. The axis.
Yes. I'm
Oh,
telling
yeah.
them, one of these numbers is used in the axis and one's in the range. Which one am I going to use here? 7. So you type x equals 7.
I think on number 7 they give you the x equals. The first graphing parabola problem, I think they try to make it easy for you by giving you the x equals. But none of the others give you that. You have to type it in yourself.
The domain is that negative infinity to infinity.
So,
I'll type that in. Wait, we haven't done the range yet.
a domain, I know I need to.
Negative infinity, comma, infinity, close parentheses. Check your answer.
Okay, now let's switch. So here's my parabola. It was opening upward. I just want something to point at. So there's the parabola we drew, and the vertex was at 7, -1. So I'm thinking my way through this range matter. So the range uses that y coordinate. Is this y coordinate corresponding to the maximum y value or the minimum y value? Is this vertex the high point or the low point on the graph? A low point. So -1 is the minimum y value. It's the smallest y value on that graph. And remember, interval notation goes small to big. So -1 is the small y value, and then it starts going up. So how do we indicate that? It's pointing up to where? Pointing up to infinity. Good. So the range is...
Put it in your little blank.
Oh, yeah, I have a blank up here. I forgot about that. -1, comma, infinity. There.
So the x coordinate of the vertex is always in the axis. The y coordinate is always in the range. The domain is always negative
All
infinity,
real
comma,
numbers.
infinity.
So
Type this in bracket.
-1, comma, infinity, parenthesis.
Okay.
And there are some applications while we're thinking about these quadratic functions. I think we should look at the applications. There's another one, number 10, that I want to look at. I think it's number 10.
This one's an easy one.
This is an easy one. The figure shows the graph of a quadratic function. Use it to determine the minimum value of f of x. Well, they say we have a minimum. Well, this parabola is opening upward, so does the vertex correspond to a maximum or minimum? It is a minimum. So yeah, it's a sensible question. What is the minimum value of f of x? That f of x is the same thing as y. What's the minimum value of y on that graph? What's the smallest y value? That +4. -4 is the x value. If they wanted the vertex, we'd type x equals. They don't ask for the axis, but if they did, we type x equals. Can y'all tell what that x coordinate is at the vertex?
If they're asking for the axis.
The axis, that's where you would use -4. The range used the y coordinate of the vertex. Any questions there? The minimum value of the function is the y coordinate, not the x coordinate.
Now 3-word problems.
They are all asking for either maximum or minimum values. If you're looking at a parabola, whether it's opening upward or downward, where would the maximum or minimum value have to occur? If there's a maximum or minimum, it has to occur where? at the vertex. So my advice to you for these word problems, use the vertex formula and find the y-coordinate, because they're always going to either be looking, if they ask you to find a maximum, that means the parabola is opening downward. So you find the vertex and the y-coordinate. If they ask you to find a minimum value of a quadratic function, that means the parabola is opening upward. The minimum occurs at the vertex.
So what you're saying is they're going to be doing this.
That vertex portion, that's right.
That's all you do for these word problems. The easiest word problems you'll ever see. Maybe not really, but
No,
we're going to
I was going to
pretend.
say that. Okay.
Number 11.
A woman has a taco stand. She's found that her daily costs are approximated by C of x equals x squared minus 40x plus 640, where C of x is the cost in x dollars to sell x units of tacos. This is called a cost function in a business environment. Find the number of units of tacos she should sell to minimize her cost. And what is the minimum cost? Let me write that function down first. This is number 11. C of x is equal to x squared minus 40x plus 640. And they're asking us to find the minimum. Okay, switch to my paper.
X is the number of units of tacos.
Oh
So
yes,
remember
I
that.
should make a note that x is the number of units of tacos.
And C of x, which is y, that's going to be the cost.
Okay, we want to find the minimum when x is the number of units of tacos and C of x is the total cost of operating her taco stand. They're asking us to find a minimum. Now, if a parabola is opening, let's say a parabola is opening downward. If a parabola is opening downward, there isn't a minimum y value. It just keeps getting smaller and smaller. So if there's going to be a minimum, that parabola had better be opening upward. If you're going to have a minimum, it better be opening upward. We don't have to draw this graph, but we need to convince ourselves, is this parabola opening upward? What's my A value? A positive 1. A is a positive 1. So yes, that graph does open upward. That means there is a minimum, and the minimum occurs at the vertex. So we'll use the vertex formula. What's B? So using that little vertex formula, we get x equals so we have the opposite of negative 40. And what am I going to write right here? 1. That A value is a positive 1. Negative, negative, the opposite of negative 40 is a positive 40 divided by 2. We get 20. Is that $20? Is that the cost of operating the taco stand? What does X represent? Is it dollars? No, it's the number of units of tacos. If this person is trying to minimize costs, then they need to sell 20 units of tacos. I don't know what a unit is. Maybe it's a dozen. Probably, what do you think she classifies it as? I don't know, but surely it's not just 20 tacos. Okay? So that's the number of units of tacos.
Maybe it's an order authority.
An order, well, I don't know. I think maybe it's a really big thing, you know, and it's a gross. So 20 gross of tacos, that'd be good. She'd have a good business then. But okay, so we know the X value. She needs to sell 20 units of tacos. What about the Y value? How do we find the actual cost? How much money is she going to have to spend to run that taco stand? Once you know X, you plug it in to find Y. So you plug in the 20, plug
Should we
in the
expect
20.
any negative answers on this problem?
No.
Would it make sense to have negative tacos?
And it wouldn't make sense to have a cost that's negative. The lowest cost you could possibly have is 0. To have a negative cost, what would that mean? They're giving you money?
Yeah. They'll give you tacos and money at the same time.
No, that's not going to happen. 20 squared is 400 minus 40 times 20 is 80. And we have that, not 80, pardon me, 800 and a plus 640. 400 minus 800 is a negative 400 plus 640. What are y'all getting there? 240. No, to B. Look at the little person, how yellow it is. Look at the screen. I'm telling you, look at the computer display. And then you see it's white where the little shadow is. And now there it's yellow. That screen projects everything as real yellow. It projects white as yellow. Y'all saw it. We're not crazy. We have witnesses. They saw it, and it's been like that for over a week now. So
Put it back on ours.
Okay, I'll put it back on ours. But how will they know if it's fixed or not?
Well, then they'll put it back for them.
I'm not going to. Okay.
Saying he's not going to post this video.
Y'all see the yellow there? Y'all see? But look, if we project from here, then there's no yellow. Should I show you? You see, the white is white when we use this computer. But, pardon me? Oh, around 4:30. Oh, okay. Until it's fixed, this one's working. Yeah, I'm enjoying being over here and turning that area. They're the peanut gallery now. Normally, this area over here is the peanut gallery, and we're over there. But still, okay. Thank you. Thanks. Oh goodness. So did y'all follow? We found our x value using minus b over 2a. That told us that she should produce and sell 20 units of tacos to minimize her cost, and then we plugged it in to find out what her minimum costs were, $240. So,
and that's what you do for every one of these word problems, minus b over 2a, then plug it in. It'll magically get you the answer.
It's not magic, it's algebra, Tony.
I know.
Okay, any questions on number 11? Number 12. There's something wrong, not wrong, but there's something I don't like about this mosquito formula. The number of mosquitoes, M of X in millions, depends on the rainfall in June. The function that models this phenomenon is M of X equals 4x minus x squared. Find the amount of rainfall that will maximize the number of mosquitoes. And what is the maximum number of mosquitoes? So X, let me make a note. X is the number of inches of rainfall.
That'll be the first answer, the minus b over 2a.
I guess that's one good thing about the drought. We don't have that many mosquitoes, do we? I'd rather have mosquitoes than have drinking water. I mean, seriously, if the water level falls, we're going to start losing water pressure. And that
does anyone live in Mathis?
Is there anyone here from Mathis? They're going to be in the state that we're going to get there in the middle of next year, but they're going into that emergency state come
November is what I read in the
Caller Times.
Yeah, something.
So M of X is the number of millions of mosquitoes. Okay, this is tricky, be careful. What's my A value?
Don't say 4.
A is the coefficient of the x squared variable, so what's A? -1. This, I guess we could rewrite this as negative x squared plus 4x.
But it's
Easier to plug it in using this format, so I'm going to leave it like that. But realize the a value isn't the number in front of the first letter you see. It's the number in front of x squared, which is a -1. With that in mind, what's b? That number in front of x, that's a +4. Hey, if we were to draw this graph, do we expect the parabola to open upward or downward? We expect it to open down. And if a parabola opens down, do you have a maximum or a minimum? A maximum occurring where? At the vertex. They better have asked us to find a maximum. Is that what they asked for? Yes, they asked for a maximum. Okay. We have a max at the vertex. So let's use our vertex formula. X equals -b over 2a. What number am I going to write here?
-4.
So you have the negative, and then you write that 4, so you have -4. 2 times, what number goes here? Okay. 2 times -1 is just a -2, so we have -4 divided by -2. What is that giving me? -4 divided by -2 gives me a +2. Is that 2 million mosquitoes? What is X representing? The inches of rain. So, if you're going to, what is this, a maximum? We're looking for a maximum. The maximum number of mosquitoes will occur if there are 2 inches of rainfall in June. 2 inches of rain.
Now, how many mosquitoes are there going to be?
How do you find? We know the x coordinate. How do we find the value of the function, the y coordinate? Plug it in. Okay, so y equals 4 times, we're plugging in the 2. Okay, so that's what, oh yeah, I forgot my square. That's 8 minus here. 8 minus 4 gives us 4 million mosquitoes in that area.
But I just typed in the 4, right? I think every word.
In England, don't they call those things mozzies or something like that? I hate that. I do not like that slang. Just say mosquitoes. Just like calling shots a jab. There's all these things in British terminology that just annoy me, and I don't know why. So if you want to raise my blood pressure, start using British slang.
One more,
and then we'll go back to piecewise functions. I guess that's another reason it's good to teach in the afternoon. We wouldn't have been able to do this morning with the internet outage, but it looks like things are working fine now. If an object is projected upward from ground level with an initial velocity of 80 feet per second, then its height in feet after t seconds is given by s of t equals -16 squared plus 80t.
t squared plus 80t.
What did I say?
-16 squared.
No, -16t squared plus 80t. Find the number of seconds it will take to reach the maximum height. What is the maximum height? A function of this nature is called a position function, and it is standard to use it's just standard practice to use the letter S to indicate a position function.
And T for time.
So it's clear why you're using a T for time, but why do they use an S? I don't know who decided on it.
But why not use an S instead of T? S for seconds and P, but you don't want to use an S variable anyway.
I know. I don't like using an S because it looks too much like a 5. Okay, negative 16t squared plus 80t. What letter is acting like x? T. So t is time in seconds. T is time in seconds.
So this thing's being thrown up, it's going up.
And then the S of t gives the height. That negative 16t squared, whenever something's projected upward without the power of a rocket, there's always a negative 16t squared included in the function. That's a result of the acceleration, because it's going to go up and up and up, and eventually what's gravity going to do? Gravity's pulling it down, and so it slows as it goes up. It's getting slower and slower, and then what does it do? Comes back down. That negative 16t squared, that's a result of the acceleration of gravity, 32 feet per second per second. This 80 times t, it's thrown initially at a rate of 80 feet per second. Distance equals rate times time. That's what that 80 times t is.
You're just talking.
I'm just talking. That's unnecessary for the problem. I'm waiting for y'all to tell me, is this parabola, if we were going to graph it, would it open upward or downward? Down, because what's my A value? Negative 16. And my B value is 80. So we're using our vertex formula. Instead of x equals, it's a t equals negative b over 2a negative, what am I writing there on top? In the parentheses? Oh, this isn't going to go in evenly, is it? So that's a negative divided by negative. That's going to become a positive. 80 divided by 32. 80 divided by 32. 2.5. This is one of those times that I would use decimals, because I bet you they let you.
Yeah.
Can you enter a decimal?
No, I think they'll let me.
I think a time more is 2.5, 2.5 seconds, rather than we could cancel a 16 above and below and get 5 halves. But who talks about time as 5 halves seconds? I think 2.5 seconds is better. There it is. So how do we find that maximum height? The thing goes up for 2.5 seconds. It's getting slower and slower. It reaches that maximum height, and then it starts to fall. How do we find that maximum value? Plug in the 2.5. So we're plugging in 2.5. This is one of those times when Tony should take his old calculator and have it ready, okay?
Ready
To punch the stuff in.
I've already done it.
2.5 times 2.5, is that 6.25 times negative 16 plus...
Oh, God. 80 times, that would be...
A 60,
I can do that.
I can do that's 200, isn't it?
It would be 160 plus half of 80, so 200. It's going to... So, 300... No. Negative 300 plus 200. 100. Just write it down. One of the times, plug it into your calculator.
And we get that thing, the maximum height, that little projectile went up, was 100 feet.
So,
any questions or comments there?
Punch that in. Oh, wait. I think we're through with my little...
Punch in the 200. I mean the 100.
100. So the rocket, or the whatever it is that's being projected up, it goes up for 2.5 seconds, reaches a height of 100 feet, and then it goes down. And after 2.5 seconds,
it hits the ground.
Mm-hmm. Any questions on this?
The second topic in this class is piecewise functions, and we don't have a piecewise graphing tool with built into this course, so we're going to handle it just by multiple choice questions when it comes to graphing. But first of all, we're going to do two things with piecewise, really three things. I'm going to define what a piecewise function is, and then we're going to evaluate piecewise functions, and then we'll draw the graphs. So here we go. Let's start with piecewise functions.
See that to scare them.
Okay, good. You're showing it to really scare them. I can tell they're scared.
I can see
Piecewise functions. Oh, shut up, Tony. Piecewise functions. A piecewise function, I'm going to do something I'm sure you were taught not to do years ago. I'm going to use the word that I'm trying to define in the definition. A piecewise function consists of two or more pieces defining the algebraic expression. I'll say an algebraic rule with two or more, I'm not going to use the word pieces, with two or more parts. Yeah, okay. An algebraic rule with two or more parts. Okay.
We're just going to jump into all the
We're going to do two things. We're going to evaluate piecewise functions, and we're going to graph them. Evaluating is very straightforward.
And just to make sure that y'all were, I want to make sure y'all did this the last time. With a function, each x value has how many y values? With a function, each x value is paired with...
Can you have 1, 7 and 1, 2 both as ordered pairs and it be a function? No. Each x value is paired with one and only one y value. Here, this function consists of three pieces. Look at that first. Let me write it down, then we'll discuss what it's saying.
H of x.
I'm going to use colored ink.
There's three different pieces here. The first piece
is negative 5x minus 18, and we're going to use that first piece if our x values are less than negative 3.
So like negative 4, negative 5, negative 6.
The y value in the middle piece will be 3, and you use that if the x value is between negative 3 and positive 3, including negative 3, but not including positive 3. I don't like that middle piece, okay?
Yeah.
And the third piece, x plus 5, for an x value greater than or equal to 3. Let me make sure I didn't miscopy this. X 3. And they want us to find just 3 of h of negative 7, h of 1, and h of
3, and h of positive 7.
Oh.
It's 4 pieces. 4 numbers.
Okay, switch to my...
Giving us these 4 numbers to plug in.
You can't just plug them into all 3 pieces, because for any x value, there can only be one y value. If you tried to plug in that negative 7 here, negative 7 plus 5 would give you a negative 2. If you plug that negative 7 in up here, you'd have a 35 minus 18. That would be a positive 17. You'd have 2 different y values, so it wouldn't be a function. You have to figure out where does the x, or which inequality is satisfied by the given x value. Our x value in the first one is negative 7. Is negative 7, our x value is negative 7. Is negative 7 less than negative 3? Is negative 7 between negative 3 and positive 3? Or is negative 7 bigger than positive 3? Which inequality is satisfied by that x value of -7?
I'll get you going. -7 is not bigger than 3.
+3. It's not this one. -7 isn't bigger than +3. Is -7 between -3 and +3? No. I think -7 is less than -3. So you're going to use the green piece. -5, plug in your -7 minus 18. That's 35 minus 18, which gives me a +17. So h of -7 is equal to 17.
Every x value,
There's one and only one y value. Okay. Now the next one, h of 1. My x value is 1.
by the way, every time you see 2 less thans or 2 greater thans in the same statement, read it as between. This red statement, x is between -3 and 3. If you read it like that, the people are going to think, wow, they know some algebra. If you read -3 less than or equal to x less than 3, they're going to think, what the heck is it? Does he even know what that means? It means between.
So, which inequality is satisfied by the given x value? The green one, the red one, or the blue one? Only one of them can be satisfied. The red. 1 is between -3 and +3. So I'll go over here to plug in for x, and there isn't an x. This piece here is nice because it's a constant function. The y value is just a 2.
No, a 3.
A 3. Where did I get 2? When x is 1, the y value is 3. This third part is interesting. What's my x value? My x value is 3. Which inequality allows 3 to be included? I see 2 of them that mention a +3. Which one includes equality? The blue one. There's that horizontal bar. X can equal 3, so the blue piece is the one we plug in. We replace the x with a 3 plus 5, which gives me a y value of 8. I haven't been boxing in my answers, have I? 17, 3, 8. What about my fourth piece? What's the x value? 7, okay. Is 7 less than -3? Is 7 between -3 and +3? Or is 7 bigger than +3? Green, red, or blue? It's the blue part, it's bigger. So you plug in the 7 plus 5, give me a final answer of 12. To evaluate piecewise functions, you have to decide which piece is satisfied, and that's the piece you plug in. You can't decide, oh, I'm going to plug in 7 here and down here, because you'll be getting 2 different y values. For any x value, there can only be one correct y value.
I remember years ago a student asking, do we need all that stuff with those less than and greater thans? And why is that important? And I was like, well, yes, of course it's important. You don't know which one to plug into if you didn't have those. That. You can't have a function like that, because then each x value is being assigned 3 y values. Okay? So this stuff here with those less than or greater than, I've got to type them all in. So call them out as it is.
17, 3, 8, and 12.
Okay. Any question? Plugging these in.
Okay, I have a question for y'all. Switch back.
Okay.
I'm just going to see if they follow this. What's h of 0? Suppose they'd asked us for h of 0. What's the x value here? 0. Okay, the x value is 0. Which piece would you use? Green, red, blue. Red. 0 is between -3 and +3. So we would use, there's no variable to plug in, it's just a constant 3. What about h of
2.999.
Okay, how about that? H of 2.999. 2.999. Is 2.999 less than -3? Is it between -3 and +3? Or is it bigger than +3? It's still between. To the naked eye, 2.999 would look like 3 on the x-axis. So, but the y value is 3.
If you wanted h of actual 3, it would be 8.
If you want h of 3, it's 8. But 2.999, to the naked eye, if I told you label that on the x-axis, it would look like you're labeling 3, wouldn't it? And the y-coordinate would be 3 in that case. We'll see. That's going to become significant with what we're about to do.
Let's graph.
Let's graph quadratic function. I mean piecewise function.
Let's see, which one do y'all want to do? 6? Is that the best one to start with?
Yeah, I think so.
These are multiple choice.
Graphing piecewise functions.
So you're going to label each piece a different color.
But I'm going to start with the top and work my way down, okay? So let's see. I'm going to use 3. Let me write the problem down. F of x equals, I'll use green for the 2 plus 3x if x is less than -4. And I'll use red for the middle part, -2x, if x is between -4 and +5, including -4 and +5. And the last one, I'll use blue, 2x for x values greater than +5.
So looking at your your equation, move it up.
I'm going to, let's see there.
I bet you'll have enough room.
We'll see. I need to write real small. To graph piecewise functions, I'm just going to plot points. I'm going to choose x values and plug them in and generate y values and plot points. But I'm not just going to start randomly choosing x values. We're going to intelligently choose the x values that we're using. I'll tell you how we're going to do it, and once we've got the graph drawn, then I'll explain my justification. Now, y equals 2 plus 3x, y equals 2 plus 3x, y equals -2x, y equals a positive 2x. What sort of graph do I expect to get from each of those individual pieces? Y equals mx plus b. What sort of a figure do you expect from each of those individual pieces? There's no exponent, so it's not going to be a parabola. No absolute values or square roots. What's the first thing you learn to graph?
Starts with an L.
A line? Yes, these things are linear. What's the minimum number of ordered pairs you need to draw a graph?
A line.
A line. I mean, to graph a line. What's the minimum number of ordered pairs you need? 2. That's what I'm going to do. I'm going to get 2 points for the green piece, 2 points for the red piece, and 2 points for the blue piece. Okay. I'm going to make my table of values for the green piece in green ink. I'll make my table of values in the red piece in red ink, and the blue piece I'll use blue ink. But since you're using the same color ink or lead, you're not changing colors the way I am, I highly recommend you number the pieces. We're about to make table number 1. I'm making table number 1, and we need 2, we're going to have to generate 2 ordered pairs. I like to be able to refer to these numbers here in the inequalities, and there's no real number, a word for them, but I think the word cut point is a good name for them, because the green piece is cut off at -4 and becomes the red piece. The red piece is cut off at what number to become the blue piece? 5. Okay, at 5 it changes from red to blue. What I'm going to do is I will automatically start with the cut point. Whatever number appears there in the inequality. And you might be thinking, wait a minute, x can't equal -4. That's right. This cut point at -4 doesn't allow equality, so we're going to use an open circle. We'll discuss why once we've drawn the graph. I'll explain that.
Cut points, and they're behaving like cut points.
They're behaving like solution cut points. There's no equality, so once we find the ordered pair and plot it, we're going to label it with an open circle.
Because even though you can't plug in -4, you can darn sure plug in -4.00001.
We'll discuss that in more detail once I'm through drawing the graph. Next, plugging in the -4, we get 2 plus, this is my scratch work here, 2 plus 3 times -4, that's a 2 plus a -12, that gives me a y value of -10. Now this first point, it's a cut point. It's going to be labeled with an open circle when I'm drawing the graph. The second one, you have to choose an x value that's actually less than -4. You don't have a choice on the first point you plug in, or first number, but you choose the second number. Choose a number that's smaller than -4. Could I use 0? 0 is my favorite number to plug in. Could I use 0? Is 0 smaller than -4? Maybe I could use a -5. I could use -10, -6. I'm going to use -5. Okay?
Don't move too far away, because you might get y values that are too big or too small.
Is -5 a cut point? Is -5, this number we just chose, is that a cut point? On the green piece, there's only one cut point. Where is it? At -4. So this number you choose yourself will always be a regular closed dot. You don't have open circles floating around at all the points you choose. If you're choosing the x value yourself, you're choosing it because it satisfies the inequality, so it's going to have to be a regular closed dot. Plugging in -5, we're going to get a 2 plus 3 times -5. That's a -15 plus 2. I agree with -13. Okay, I guess I'll put parentheses around it to make a note. These are ordered pairs that we found.
You know what? Maybe when you're through setting up the points, you should draw the graph right here.
That's what I was going to do.
Okay, good thinking.
Okay. I think I'll make all 3 tables of values and then start drawing. Okay. I'm going to now make the red table. This is table number 2. Remember, I said we're plotting points, but we're plotting the points intelligently. We're not just randomly choosing x values to plug in to each piece. You must start off with any numbers that appear within the inequality. You must start off. In this case, there's no free will. You don't choose a point yourself. You have two cut points appearing in the inequality. You must use -4. You must use +5.
They both have equal signs.
They both have equal signs, so these are regular closed dots. The only time you have an open circle is when you're plugging in a number, a cut point, for which there's no equality. That's the only time you'll have an open circle on the graph. Plugging -4 into the red piece, we get -2 times -4. That's giving me a y value of 8. Now we plug in +5. 2 times -2 times +5 gives me a y value of sign. No, I think it's -2 times 5. Is it a negative? -2 times 5. That's a -10. I wrote down +2, but then I corrected it. And one last piece. Table number 3. We're making all 3 tables of values, and then we'll draw the graph.
How many blue cut points do we have?
Hey, a number on the second table, we didn't choose a number on our own. We had to use -4 and +5. Am I going to have to choose a number to plug in for this third piece? Yes? Okay, what should be the first number I use for x in that third piece? You have to use the number that appears within the inequality. You've got to plug in 5, and we'll discuss why once we're through drawing the graph. But there's no equality. So to indicate you're plugging in an x value for which there's no equality, you're plugging in a cut point with no equality, it'll be labeled with an open circle. Now we're also going to need another number, a number bigger than 5. Could I use 0? 0 is my favorite number to plug in. Can I use 0? No? What's the smallest integer I could use to plug in? 6. I could use 6. 6 is bigger than 5. Could I have used 4 here? Could I have chosen? Could not use 4. I have to use a number bigger than 5. The number or numbers that you choose on your own must be regular closed dots. 6 satisfies that inequality. Hopefully you understand why we're using an open circle. We're plugging in a number that doesn't satisfy the inequality. 5 isn't greater than 5. 5 is equal to 5. But down here, the number you choose must satisfy it, so it will always be a regular closed dot. Plugging in 5 into the blue piece, what are we getting? 10. Plugging in 6, what are we getting? 12. 2 times 6, I agree. Now, I don't do this that often, but I'm going to draw my grid, my XY grid right here. And let's see, we have -13 as a Y value. What's the biggest Y value? 12? Oh, okay. I'm going to have to go about 13 units up and 13 units down. Be sure to label the cut points on the x-axis. You got to clearly label 5. 1, 2, 3, 4, 5. Why am I using blue? I should be using black. What's the other cut point I need to label on the x-axis? -4? Yes. You need to clearly label -4 and +5. Because it's at -4 that the green piece is going to change to the red piece. It's at +5 that the red piece is going to change to the blue piece. So let's see. 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. O. I guess there. That we'll make it work. Don't worry, we'll make it work.
Okay.
Okay, I'll show you how I'm going to make it work. I'm going to do a there. Now it's going to work.
Wait, let me see if I need to. Think I should.
Try focus and make sure. Does that look focused to y'all? There, okay. First piece, the green piece, we go to -4, -10. We're going to have an open circle there. So, 1, 2, 3, 4,
Negative
6.
10.
Oh, -2. 1, 2, 3, 4, 5, 6. So we go to -4, -10, and we have an open circle. At -4, -10, we have an open circle. Then at -5, we go down 13 units. Is that on there? I'll do it like that. So -5, we're going down 13 units. Is this going to be an open circle? A regular closed dot. You start at the cut point and you go towards the secondary point. Realize x less than -4. It starts at -4 and it goes to the left. This graph continues going. It's going down, but it's also going to the left. You have an arrowhead on the left-hand side. The interval keeps going forever and ever. Moving down, it'll hit that graph. This is called an open ray. The starting point is an open circle, and then it goes forever in one direction. By the way, here's something to think about. You can't. These things are functions, so they have to pass the vertical line test. You can't have arrowheads just flying everywhere, or else the things wouldn't pass the vertical line test. Moving to the second
Arrow
piece
should only
be on the leftmost or on the rightmost. It can keep going. One piece can keep going forever on the left. One piece can keep going forever on the right. Now the second piece. Okay, the red piece. -4, 8. So we're at -4 again, but we got to go up 8 units. 1, 2, 3, 4, 7, 8. -4, 8. We have a regular closed dot there. And then +5, -10. +5, -10. You have another closed dot. I guess we've given away the answer to this next question. You start here. You go there. Technically at 0, 0, it should be passing through the origin, but I sort of missed it. So, let's see. There.
Notice the red piece should start at -4 x value and end at +5 x
There are
value.
no arrows. This interval, does this interval keep going and going in any direction? No. It starts at -4, it ends at +5. There are no arrowheads on this piece. That middle piece is just a closed line segment. A closed line segment is a line segment that has two closed circles as the endpoints. Any questions there?
So you've drawn the green piece, you've drawn the red piece.
All that's left is the blue piece. We go to the point +5, +10, and you have an open circle there. At +5, +10, we have an open circle. Then at 6, we go up 12 units, so that's right out here. And that's a regular closed dot. The points that you choose yourself must be regular closed dots. You start at the cut point, and it starts going, the interval x greater than 5 keeps going forever to the right, so the right-hand side of the graph keeps going forever. There are arrowheads there. And notice this thing passes the vertical line test. You say, well, what about here and here? We have 2 points stacked on top of one another. That's why this thing is open. You could draw a vertical line, and it would only hit the graph in one spot. It hit the graph here, but down here, there's not a point there.
Open circles mean don't include it.
Likewise, you can't have two stacked solid circles, and we don't. We could draw a vertical line. It would pass right through that open circle. It wouldn't be hitting the graph, but down here it would hit. This is a function. It passes the vertical line test. Let's choose the correct answer. And then I want to talk about why are we plugging in -4? Why do we plug in +5? -4 isn't less than -4. 5 isn't bigger than 5. Let's see. A, B, C, or D. Start blowing it up.
No, let me do it like this.
Is that it?
I'm thinking that might
No, I think that's it.
Notice each unit is 2. 2, 4, 6. So 5 is right out there. I'm thinking that's it, but let's discard the others.
Clearly not that one. What about the third one? Clearly not that one. I don't even think that comes close. The only one that comes close is response A. And notice the way they're showing those closed dots at the beginning and end of that line segment. The arrays have open circles, but
I've had students before ask me, wait a minute, why doesn't it show this dot right here? The one you chose. It doesn't show that, and it doesn't show this one right here, the one you chose.
They don't know which dot you're choosing. You could have chosen any number bigger than 5 for the blue piece. You could have chosen any number bigger than, smaller than -4 for the green piece. They're not showing the secondary points because you're choosing those yourself.
Okay. You can grasp how to if you know
now,
how to graph a piecewise function, you know a lot about graphing.
Okay. I think for our discussion, it's easier for you to see why we used 5 rather than with the -4. The real number system is dense. Between any two real numbers, there are infinitely many real numbers. For example, I claim that there are infinitely many real numbers between 5 and 5.1. You say, well, how are there infinitely many numbers? Well, is it 5.01 between those two? What about 5.001 or 5.0001? It's getting closer and closer to 5, but you could keep doing this forever. There are infinitely many real numbers between any two given numbers. Now, do you agree that 5 is not bigger than 5? 5 is not bigger than 5. I claim there are infinitely many numbers that look like 5 on the x-axis. For example, 5.01. 5.01 is bigger than 5. That means 5.01, I should be using blue, I guess. 5.01, if we plug that into this blue piece, we're going to get a 10.02. Is that right? This ordered pair is clearly on the graph. You have to show this point. 5.01, 10.02. That point's on the graph. Let's come over here and plot it. If you wanted to plot that 5.01, 10.02 to the naked eye, I'm pointing at it right now, but to the naked eye, what does it look like I'm pointing at? What ordered pair does it look like? This ordered pair looks just like what? The ordered pair 510. That's why we put an open circle there. That open circle is saying 510 is not on the graph. but there are infinitely many points right there that look like 510. To the naked eye, it looks like 510 if you plotted it, and those points are on the graph. That's why you have to plug in that cut point 5 and that cut point -4. Even though they don't satisfy the inequality, this the green piece, there are infinitely many points. When you start plugging in -4.001 or -4.0001, they're all less than -4. They all satisfy the inequality. And so those points are on the graph. While -4, -10 is not on the graph, there are infinitely many other points right there that look like -4, -10 that are on the graph. So that is why you must start with the cut point, even if there's no equality. But if you're plugging in a cut point without equality, you indicate that using an open circle. Any questions there?
So this is like a two-dimensional cut point.
That's exactly right, Tony. And with that intelligent statement of yours, I'm going to what number was this? I didn't even write down this number.
That was number 6.
Number 6, okay. Now I think I'll let Tony do the next one. Seems like I've been doing all the talking. I'm going to let my voice rest.
I think I want to do 3 first.
Yeah, 3's a good one.
No, I'm going to go ahead and go the order I had written to do. I'll do number 5 first.
Oh, stop. That's great. Oh.
So,
number 5 looks a little easier for no reason other than there's only how many pieces here? Just 2 pieces.
we have f of x equals -3 if x is less than or equal to -1 and -1. Oh, now why are they using -1 so much? X is greater than -1. Problems where the same number appears several times is not always a good thing. Okay, so we are going to have 2 pieces this time. And do y'all remember, what do you call a function if there's nothing, no x to plug into? Starts with a C.
It's a constant function. I don't think we defined that. I did say one time, oh, that piece is constant, but I don't think I ever defined it.
Oh, okay.
In the discussion.
Okay, so we're going to just plot off or start with our points. Oh, wait, y'all can't even see what I'm writing here. So we're going to have what color is that? Brown and blue. So we're going to do the first one. I'll call this rule 1 and rule 2. Rule 1. I set up my XY table. First number we must plug in is that cut point, and we'll have an open or closed circle. Closed. So I'm going to plug a -1 in for x, and it's going to have a closed circle. And then I'm going to need another number that's less than -1. Number smaller than -1. Don't say 0. -2, -3, -4. I'm going to go ahead and use -2. And that will be a closed dot too. The only time you can have an open circle is at a cut point. Now, this is called a constant function because it doesn't matter what x is.
If I plug in -1 for x here in the Brown function, I'm still just going to get -3. See, the y value is -3. It doesn't matter what the x values are. This one's a little bit easier than the first one, the one we just finished doing. Having seen me do those points, could y'all do the blue XY table? You know what, if you want to, you could go ahead right off and plug in the y values. What are the y values? This is a constant function. Every y value is -1. Okay, what number must he first plug in for x, or use for x? Got -1 from the inequality. That's a cut point. How will it be labeled? Open circle. Then we need a number bigger than -1. What's my favorite number to use? 0. Is 0 greater than -1? Yes, it is. Will that be an open circle? Say no. No, 0 is not. You only use an open circle when you're plugging in a cut point that doesn't allow equality. The number you choose must satisfy the inequality. You wouldn't be using 0 if it weren't greater than -1. So your secondary points that you choose must be regular closed dots. Oh wow, this one's so nice. The numbers are nice and small. I don't need small numbers, Tony. I can make it work even with large numbers. Okay, so I'm going to graph the brown part. We're going to have a brown graph and a blue graph. They're changing. It's cutting off at -1. So I'm going to go ahead and label -1 right here on the x-axis. That's what's going to change from one graph to the other. So left 1, down 3, close circle. Left 2, down 3, a dot that looks like a closed circle. The graph starts at the cut point, starts here, and then it goes and keeps going to the left. That interval keeps going, x less than -1 keeps going to the left, so the left side of the graph has the arrowheads. Now we draw the blue part of the graph. I hate to say it, Tony, but the blue and black look the same to me. Does it look different to y'all? You know, tell the change in color. Oh, this ain't black, it's brown. Oh, well, it looks black. Black and a paler shade of black. Okay, I'll use red for this. Okay, so left 1, down 1, open circle. Over 0, down 1, just a dot. It looks like a closed circle, doesn't it? You start at the cut point, and it's going to the right forever. I'll put a little arrowhead. The only way you won't have an arrow on one piece is if the inequality is like that middle piece in the previous problem, where there's a starting point and an ending point. Everyone else, it's going to have an arrowhead, and the arrowhead will be going in the direction that the inequality is pointing. The inequality is pointing to the left, keeps going to the left. The inequality is pointing to the right, it keeps going to the right. Now choose the answer. A, B, C, or D. Oh, move that line out. A, is that it? Pay careful attention to the open and close. No, I think they haven't messed up there. They've reversed the open and close, so that's not it. B, not even close. C,
Is that it?
I think that's it. Open on the top, closed on the bottom. Let's just look at D to discard it.
No.
No, not D. So you're right. Response C. Any questions?
They're not all as involved as question 6. But question 6, the first one here, the three-piece one,
Illustrates it the best.
yes.
The thought process.
If you can follow this one, then you know how to graph a piecewise function. Let's do
Okay.
number 3. Write number 3 down. 3. F of x equals, I'll do like the old or the old movies where they used red and black because they stood out so well. So we have the rule, we use the piece x minus 4 if our x value is less than or equal to 1. And we use just the constant function, negative 3, if x is greater than 1. Okay. Well, we'll start off making our little tables. 1, 2, here's table 1.
What's my cut point? Where does the black piece change to the red piece? At what x value? What did you say? 1. I
That's
agree.
right. So 1. There's an equal sign, a black equal sign.
Be careful, that's just a dot there.
Yeah,
it's
my-
a positive 1, not a negative 1.
Yeah,
That
my
is a positive 1.
And so, open or closed? Closed, okay. And we need a number less than 1.
What's my favorite number to use? 0. Can we use 0? Is 0 less than 1? Yes, okay.
And it's just going to be an old dot. Looks like a closed circle, doesn't it?
Plugging in 1 into the black piece, what are we going to get?
4. 1
Negative
minus
3.
4.
1 minus 4, I agree, is negative 3.
And then
Plugging in 0, what are we going to get? Negative 4. Now let's make the second table.
now it's a constant one. Second table. But that, I mean, is it clear how I know that the y values never change? You see, the y is just negative 3. There's not an x there. So I can go ahead and fill those in. Negative 3. What's the first x value I've got to use? I've got to start there. 1 with an open or closed circle. Open. Then I need a number bigger than 1. 2. And it will just be a plain dot. This is another one that's pretty easy.
You know, it's hard to tell that that open circle is an open circle. It sort of looks closed in.
Oh,
Okay.
open circle, dot. Over here, closed circle, which is just a dot, and then a dot. I'm saying dot because the only time there's open and closed circles are at cut points, and the only cut point is at 1. So let me finish drawing this up. 1, 2, 3, 4. Oh, this one's going to be interesting. Oh, there's something, a neat thing that happens here. Okay, so right 1, down 3. Oh, let me go ahead and label 1. That's where we're changing from the black rule to the red rule. Write 1 down 3. 1, 2, 3. Oops.
Fill it in.
Yeah, fill it in. So I just plotted this point. Write 1 down 3. Put a closed circle. Now over 0, down 4. Put a dot. Over 0, down 4. A dot. How am I going to connect those? Where does the arrow go? Up here? Where does the arrow go? Here? Am I going to do it like this? Down. You start here.
You always start at the cut point and go towards the secondary point. A point that you chose yourself.
Now, why did I say this one's sort of interesting? Yes. Look at what's about to happen. 1, -3.
We go there
open
expecting
circle.
to put an open circle, but what do we see when we get there? If an open and closed circle appear at the same spot, the closed circle takes precedence. This open circle is saying, hey, that point isn't on the graph. You're right, it's not on the red graph, but it's on the black graph.
If you have an open and closed circle occurring at the same spot,
Then you have a closed circle.
Now, if you have different colors, you can try to do what I'm doing here to try to show which.
But I don't encourage that.
Yeah, okay. Write 2, down 3. I start at the cut point and go like that.
Once again, that open circle, you're saying, that point isn't on the graph. But yes, it is. It was on the graph because of the first piece. That's why if you have an open and a closed circle appearing at the same spot, your graph has a regular closed dot. Any questions there? Okay. Oh, let's see. A, B, C, or D? A, is that it?
No.
Clearly not. B?
Yeah, that's it.
I think
isn't
that's it.
Notice,
The incrementing in units of 2, right in between 0 and 2, is what?
1.
I think that's it. I think it's B, but let's discard the others.
Definitely not that one.
Definitely not. What about this one?
No.
Definitely not.
So it is B. Okay. Any questions on this? This graphing piecewise functions is, if you can do those, you know how to graph. Period. All right? And you understand a lot about graph theory. So, are there any questions you want recorded? If not, stop it.
Where is it? Oh,
I had kept moving it to get